Hello, this is Todd Booth, and I'll be giving a presentation on the book Network Security Essentials, Chapter 4. The author is William Stallings. This chapter covers two important related concepts. First is the complex topic of cryptographic key distribution, involving cryptographic, protocol, and management considerations. This chapter gives the reader a feel for the issues involved and provides a broad survey of the various aspects of key management and distribution. This chapter also examines some of the authentication functions that have been developed to support network-based user authentication. The chapter includes a detailed discussion on one of the earliest and also one of the most widely used key distribution and user authentication services, KERBEROS. Next, the chapter looks at key distribution schemes that rely on asymmetric encryption. This is followed by a discussion of X.509 certificates and public key infrastructure. Finally, the concept of federated identity management is introduced. Remote user authentication principles. In most computer security contexts, user authentication is the fundamental building block and the primary line of defense. User authentication is the basis for most types of access control and for user accountability. RFC 4949, which is Internet Security Glossary, defines user authentication as the process of verifying an identity claimed by or for a system entity. This process consists of two steps. 1. Identification step, presenting an identifier to the security system. Identifiers should be assigned carefully because authenticated identities are the basis for other security services, such as Access Control Service. 2. Verification step, presenting or generating authentication information that corroborates the binding between the entity and the identifier. In essence, identification is the means by which a user provides a claimed identity to the system. User authentication is the means of establishing the validity of the claim. Note that user authentication is distinct from message authentication. As defined in Chapter 3, message authentication is a procedure that allows communicating parties to verify that the contents of a received message have not been altered and that the source is authentic. This chapter is concerned solely with user authentication. NIST model for electronic user authentication. NIST SP 800-63-2, Electronic Authentication Guideline, defines electronic user authentication as the process of establishing confidence in user identities that are presented electronically to an information system. Systems can use the authenticated identity to determine if the authenticated individual is authorized to perform particular functions, such as database transactions or access to system resources. In many cases, the authentication and transaction or other authorized function take place across an open network such as the Internet. Equally, authentication and subsequent authorization can take place locally, such as across a local area network. Please review the figure, Authentication Architectural Model. This defines a general model for user authentication that involves a number of entities and procedures. We discuss this model with reference to this figure. The initial requirement for performing user authentication is that the user must be registered with the system. The following is a typical sequence of registration. An applicant applies to a registration authority, RA, to become a subscriber of a Credential Service Provider, CSP. In this model, the RA is a trusted entity that establishes and vouches for the identity of an application to a CSP. The CSP then engages in an exchange with the subscriber. Depending on the details of the overall authentication system, the CSP issues some sort of electronic credential to the subscriber. The credential is a data structure that authoritatively binds an entity and additional attributes to a token possessed by a subscriber and can be verified when presented to the verifier in an authentication transaction. The token could be an encryption key or an encrypted password that identifies the subscriber. The token may be issued by the CSP, generated directly by the subscriber, or provided by a third party. The token and credential may be used in subsequent authentication events. Once a user is registered as a subscriber, the actual authentication process can take place between the subscriber and one or more systems that perform authentication and subsequently authorization. The party to be authenticated is called a claimant, and the party verifying the identity is called a verifier. When a claimant successfully demonstrates possession and control of a token to a verifier through an authentication protocol, the verifier can verify that the claimant is the subscriber named in the corresponding credential. The verifier passes on an assertion about the identity of the subscriber to the relying party, RP. That assertion includes identity information about a subscriber, such as the subscriber name, an identifier assigned at registration, or other subscriber attributes that were verified in the registration process. The RP can then use the authenticated information provided by the verifier to make access control or authorization decisions. An implemented system for authentication will differ from or be more complex than this simplified model, but the model illustrates the key roles and functions needed for a secure authentication system. Means of authentication. There are 4 general means of authenticating a user's identity, which can be used alone or in combination. Something the individual knows. Examples include a password, a personal identification number, PIN, or answers to a prearranged set of questions. Something the individual possesses. Examples include cryptographic keys, electronic keys, smart cards, and physical keys. This type of authenticator is referred to as a token. Something the individual is. Static biometrics. Examples include recognition by fingerprint, retina, and face. Something the individual does. Dynamic biometrics. Examples include recognition by voice pattern, handwriting characteristics, and typing rhythm. All of these methods, properly implemented and used, can provide secure user authentication. However, each method has its own problems. An adversary may be able to guess or steal a password. Similarly, an adversary may be able to forge or steal a token. A user may forget a password or lose a token. Furthermore, there is a significant administrative overhead for managing password and token information on systems and securing such information on systems. With respect to biometric authenticators, there is a variety of problems, including dealing with false positives and false negatives, user acceptance, cost, and convenience. For network-based user authentication, the most important methods involve cryptographic keys and something the individual knows, such as a password. Symmetric key distribution using symmetric encryption. For symmetric encryption to work, the 2 parties to an exchange must share the same key, and that key must be protected from access by others. Furthermore, frequent key changes are usually desirable to limit the amount of data compromised if an attacker learns the key. Therefore, the strength of any cryptographic system rests with the key distribution technique, a term that refers to the means of delivering a key to two parties that wish to exchange data without allowing others to see the key. Key distribution. Key distribution can be achieved in a number of ways. For two parties A and B, there are the following options. 1. A key could be selected by A and physically delivered to B. 2. A third party could select the key and physically deliver it to A and B. 3. If A and B have previously and recently used a key, one party could transmit the new key to the other using the old key to encrypt the new key. 4. If A and B each have an encrypted connection to a third party, C, C could deliver a key on the encrypted links to A and B. Options 1 and 2 call for a manual delivery of a key. For link encryption, this is a reasonable requirement because each link encryption device is only going to be exchanging data with its partner on the other end of the link. However, for an end-to-end encryption over a network, manual delivery is awkward. In a distributed system, any given host or terminal may need to engage in exchanges with many other hosts and terminals over time. Thus, each device needs a number of keys supplied dynamically. The problem is especially difficult in a wide area distributed system. Option 3 is a possibility for either link encryption or end-to-end encryption. But if an attacker ever succeeds in gaining access to one key, then all subsequent keys are revealed. Even if frequent changes are made to the link encryption keys, these should be done manually. To provide keys for end-to-end encryption, option 4 is preferable. For option 4, two kinds of keys are used. Session key, when two end systems, hosts, terminals, etc., wish to communicate, they establish a logical connection, for example, virtual circuit. For the duration of that logical connection, called a session, all user data are encrypted with a one-time session key. At the conclusion of the session key is destroyed. Permanent key. A permanent key is a key used between entities for the purpose of distributing session keys. A necessary element of option 4 is a key distribution center, KDC. The KDC determines which systems are allowed to communicate with each other. When permission is granted for two systems to establish a connection, the key distribution center provides a one-time session key for that connection. In general terms, the operation of a KDC proceeds as follows. 1. When host A wishes to set up a connection with host B, it transmits a connection request packet to the KDC. The communication between A and the KDC is encrypted using a master key shared only by A and the KDC. 2. If the KDC approves the connection request, it generates a unique one-time session key. It encrypts the session key using the permanent key it shares with A and delivers the encrypted session key to A. Similarly, it encrypts the session key using the permanent key it shares with B and delivers the encrypted session key to B. 3. A and B can now set up a logical connection and exchange messages and data, all encrypted using the temporary session key. The automated key distribution approach provides the flexibility and dynamic characteristics needed to allow a number of users to access a number of servers and for the servers to exchange data with each other. The most widely used application that implements this approach is KERBEROS, described in the next section. KERBEROS. KERBEROS is a key distribution and user authentication service developed at MIT. The problem that KERBEROS addresses is this. Assume an open distributed environment in which users at workstations wish to access services on servers distributed throughout the network. We would like for servers to be able to restrict access to authorized users and to be able to authenticate requests for service. In this environment, a workstation cannot be trusted to identify its users correctly to network services. In particular, the following three threats exist. 1. A user may gain access to a particular workstation and pretend to be another user operating from that workstation. 2. A user may alter the network address of a workstation so that the requests sent from the altered workstation appear to come from the impersonated workstation. 3. A user may eavesdrop on exchanges and use a replay attack to gain entrance to a server or to disrupt operations. In any of these cases, an unauthorized user may be able to gain access to services and data that he or she is not authorized to access. Rather than building elaborate authentication protocols at each server, KERBEROS provides a centralized authentication server whose function is to authenticate users to servers and servers to users. KERBEROS relies exclusively on symmetric encryption, making no use of public key encryption. Two versions of KERBEROS are in use. Version 4 implementations still exist, although this version is being phased out. Version 5 corrects some of the security deficiencies of version 4 and has been issued as a proposed internet standard. Because of the complexity of KERBEROS, it is best to start with a description of version 4. This enables us to see the essence of the KERBEROS strategy without considering some of the details required to handle subtle security threats. Then we examine version 5. KERBEROS version 4. Version 4 of KERBEROS makes use of DES in a rather elaborate protocol to provide the authentication service. Viewing the protocol as a whole, it is difficult to see the need for many elements contained therein. Therefore, we adopt a strategy used by Bill Bryant and build up to the full protocol by looking first at several hypothetical dialogues. Each successive dialogue adds additional complexity to counter security vulnerabilities revealed in the preceding dialogue. In an unprotected network environment, any client can apply to any server for any service. The obvious security risk is that of impersonation. An opponent can pretend to be another client and obtain unauthorized privileges on server machines. To counter this threat, servers must be able to confirm the identities of clients who request service. Each server can be required to undertake this task for each client-server interaction, but in an open environment, this places a substantial burden on each server. An alternative is to use an authentication server, AS, that knows the passwords of all users and stores these in a centralized database. In addition, the AS shares a unique secret key with each server. These keys have been distributed physically or in some other secure manner. Although the foregoing scenario solves some of the problems of authentication in an open network environment, problems remain. Two in particular stand out. First, we would like to minimize the number of times that a user has to enter a password. Suppose each ticket can be used only once. If user C logs on to a workstation in the morning and wishes to check his or her mail at a mail server, C must supply a password to get a ticket for the mail server. If C wishes to check the mail several times during the day, each attempt requires re-entering the password. We can improve matters by saying that tickets are reusable. For a single logon session, the workstation can store the mail server ticket after it is received and use it on behalf of the user for multiple accesses to the mail server. However, under this scheme, it remains the case that a user would need a new ticket for every different service. If a user wished to access a print server, a mail server, a file server, and so on, the first instance on each access would require a new ticket and hence require the user to enter the password. The second problem is that the earlier scenario involved a plaintext transmission of the password. An eavesdropper could capture the password and use any service accessible to the victim. To solve these additional problems, we introduce a scheme for avoiding plain text passwords and a new server known as the Ticket Granting Server, TGS. The new service, TGS, issues tickets to users who have been authenticated to AS. Each time the user requires access to a new service, the client applies to the TGS using the ticket to authenticate itself. The TGS then grants a ticket for the particular service. The client saves each service granting ticket and uses it to authenticate its users to a server each time a particular service is requested. Please pause the video and review the table. Please pause the video and go through these steps. 1, where the user logs on. 2, the AS verifies. 3, the workstation prompts. 4, the TGS decrypts the ticket. 5, the workstation sends the ticket. And 6, the host verifies the ticket. Please pause the video and review this figure of the KERBEROS exchanges. Please pause the video and review this table. This is the second page of the same table. This is the last page of the same table. KERBEROS realms. A full-service KERBEROS environment consisting of a KERBEROS server, a number of clients, and a number of application servers requires the following. 1. The KERBEROS server must have the user ID and hashed passwords of all participating users in its database. All users are registered with the KERBEROS server. 2. The KERBEROS server must share a secret key with each server. All servers are registered with the KERBEROS server. Such an environment is referred to as a KERBEROS realm. The concept of realm can be explained as follows. A KERBEROS realm is a set of managed nodes that share the same KERBEROS database. The KERBEROS database resides on the KERBEROS master computer system, which should be kept in a physically secure room. A read-only copy of the KERBEROS database might also reside on other KERBEROS computer systems. However, all changes to the database must be made on the master computer system. Changing or accessing the contents of a KERBEROS database requires the KERBEROS master password. KERBEROS principal. A related concept is that of a KERBEROS principal, which is a service or user that is known to the KERBEROS system. Each KERBEROS principal is identified by its principal name. Principal names consist of 3 parts: a service or username, an instance name, and a realm name. Network of clients and servers under different administrative organizations typically constitute different realms. That is, in general, it is not practical and does not conform to administrative policy to have users and servers in one administrative domain registered with a KERBEROS server elsewhere. However, users in one realm may need access to servers in other realms. and some servers may be willing to provide service to users from other realms, provided that those users are authenticated. So what are the differences between Kerberos versions 4 and 5? Version 5 is intended to address the limitations of version 4 in two areas: environmental shortcomings and technical deficiencies. We briefly summarize the improvements in each area. Kerberos version 4 did not fully address the need to be general purpose. This led to the following environmental shortcomings: encryption system dependence, Internet protocol dependence, message byte ordering, ticket lifetime, authentication forwarding, inter-realm authentication. Apart from these environmental limitations, there are technical deficiencies in the version 4 protocol itself. Most of these deficiencies were documented, and version 5 attempts to address these. The deficiencies are the following: double encryption, PCBC encryption, session keys, password attacks. Summary of Kerberos version 5 message exchanges. The table summarizes the basic version 5 dialog. This is best explained by comparison with the version 4, which we saw previously. First, consider the authentication service exchange. Message 1 is a client request for a ticket granting ticket. As before, it includes the ID of the user and the TGS. The following new elements are added: the realm, which indicates the realm of the user; options, used to request that certain flags be set in the return ticket; times, used by the client to request the following time settings in the ticket from the desired start time for the requested ticket till the requested expiration time for the requested ticket; R time, the requested renew till time; nonce, a random value to be repeated in message 2 to assure that the response is fresh and has not been replayed by an opponent. Message 2 returns a ticket granting ticket identifying information for the client and a block encrypted using the encryption key based on the user's password. This block includes the session key to be used between the client and the TGS, times specified in the message 1, the nonce from the message C1, and TGS identifying information. The ticket itself includes the session key, identifying information for the client, the requested time values, and flags that reflect the status of this ticket and the requested options. These flags introduce significant new functionality to version 5. For now, we defer a discussion of these flags and concentrate on the overall structure of the version 5 protocol. Let us now compare the ticket granting service exchange for versions 4 and 5. We see that message 3 for both versions includes an authenticator, a ticket, and the name of the requested service. In addition, version 5 includes requested times and options for the ticket, and a nonce, all with functions similar to those of message 1. The authenticator itself is essentially the same as the one used in version 4. Message 4 has the same structure as message 2. It returns a ticket plus information needed by the client, with the information encrypted using the session key now shared by the client and the TGS. Finally, for the client-server authentication exchange, several new features appear in version 5. In message 5, the client may request as an option that mutual authentication is required. If mutual authentication is required, the server responds with message 6. This message includes the timestamp from the authenticator Note that in version 4, the timestamp was incremented by 1. This is not necessary in version 5 because the nature of the format of the messages is such that it is not possible for an opponent to create message 6 without knowledge of the appropriate encryption keys. The subkey field, if present, overrides the subkey field if present in the message 5. The optional sequence number field specifies the starting sequence number to be used by the client. Key distribution using asymmetric encryption. On the face of it, the point of public key encryption is that the public key is public. Thus, if there is some broadly accepted public key algorithm, such as RSA, any participant can send his or her public key to any other participant or broadcast the key to the community at large. Although this approach is convenient, it has a major weakness. Anyone can forge such a public announcement. That is, some user could pretend to be user A and send a public key to another participant or broadcast such a public key. Until such time as user A discovers the forgery and alerts other participants, the forger is able to read all encrypted messages intended for A and can use the forged keys for authentication. The solution to this problem is the public key certificate. In essence, a certificate consists of a public key plus a user ID of the key owner, with the whole block signed by a trusted third party. Typically, the third party is a certificate authority, CA, that is trusted by the user community, such as a government agency or a financial institution. A user can present his or her public key to the authority in a secure manner and obtain a certificate. The user can then publish the certificate. Anyone needing this user's public key can obtain the certificate and verify that it is valid by way of the attached trusted signature. The figure illustrates the process. One scheme has become universally accepted for formatting public key certificates, the X.509 standard. X.509 certificates are used in most network security applications, including IP security, secure sockets layer, and SMIME, all of which are discussed in subsequent chapters. X.509 is examined in detail in the next section. Please pause and review this figure on public key certificate use. X.509 certificates. ITU-T recommendation X.509 is part of the X.500 series of recommendations that define a directory service. The directory is, in effect, a server or distributed set of servers that maintains a database of information about users. The information includes a mapping from username to network address, as well as other attributes and information about the users. X.509 defines a framework for the provision of authentication services by the X.500 directory to its users. The directory may serve as a repository of public key certificates. Each certificate contains the public key of a user and is signed with the private key of a trusted certification authority. In addition, X.509 defines alternative authentication protocols based on the use of public key certificates. X.509 is an important standard because the certificate structure and authentication protocols defined in X.509 are used in a variety of contexts. For example, the X.509 certificate format is used in SMIME, in IP security, and in SSL/TLS. X.509 was initially issued in 1988. The standard was subsequently revised in 1993 to address some of the security concerns. The standard is currently at version 7 and updated in 2012. X509 is based on the use of public key cryptography and digital signatures. The standard does not dictate the use of a specific digital signature algorithm, nor a specific hash function. The figure illustrates the overall X509 scheme for generation of a public key certificate. The certificate for Bob's public key includes unique identifying information for Bob, Bob's public key, and identifying information about the CA, plus other information as explained subsequently. This information is then signed by computing a hash value of the information and generating a digital signature using the hash value and the CA's private key. The figure shows the general format of a certificate, which includes the following elements. Version differentiates among successive versions of the certificate format. The default is version 1. If the issuer unique identifier or subject unique identifier are present, the value must be version 2. If one or more extensions are present, the version must be version 3. Although the X509 specification is currently at version 7, no changes have been made to the fields that make up the certificate since version 3. Serial number, an integer value unique within the issuing CA that is unambiguously associated with this certificate. Signature algorithm identifier, the algorithm used to sign the certificate together with any associated parameters. Because this information is repeated in the signature field at the end of the certificate, this field has little, if any, utility. Issuer name, X500 name of the CA that created and signed the certificate. Period of validity consists of 2 dates, the first and last on which the certificate is valid. Subject name, the name of the user to whom the certificate refers. That is, this certificate certifies the public key of the subject who holds the corresponding private key. Subject's public key information, the public key of the subject, plus an identifier of the algorithm for which this key is to be used, together with any associated parameters. Issuer unique identifier, an optional bit string used to identify uniquely the issuing CA in the event the X500 name has been reused for different entities. Subject unique identifier, an optional bit string field used to identify uniquely the subject in the event the X500 name has been reused for different entities. Extensions, a set of one or more extension fields. Extensions were added in version 3 and are discussed later in this section. Signature covers all of the other fields of the certificate. One component of this field is the digital signature applied to the other fields of the certificate. This field includes the signature algorithm identifier. Obtaining a user certificate. User certificates generated by a CA have the following characteristics. Any user with access to the public key of the CA can verify the user public key that was certified. No party other than the certification authority can modify the certificate without this being detected. Because certificates are unforgeable, they can be placed in a directory without the need for the directory to make special efforts to protect them. If all users subscribe to the same CA, then there is a common trust of that CA. All user certificates can be placed in the directory for access by all users. In addition, a user can transmit his or her certificate directly to other users. In either case, once B is in the possession of A's certificate, B has confidence that messages it encrypts with A's public key will be secure from eavesdropping, and that messages signed with A's private key are unforgeable. If there is a large community of users, it may not be practical for all users to subscribe to the same CA. Because it is the CA that signs certificates, each participating users must have a copy of the CA's own public key to verify signatures. This public key must be provided to each user in an absolutely secure, with respect to integrity and authenticity, so that the user has confidence in the associated certificates. Thus, with many users, it may be more practical for there to be a number of CAs, each of which securely provides its public key to some fraction of the users. And in this figure, we have an X509 hierarchy. It's just a hypothetical example. And the figure taken from X509 is a good example of a hierarchy. The connected circles indicate the hierarchical relationship among the CAs. The associated boxes indicate certificates maintained in the directory for each CA entry. As you can see, the directory entry for each CA includes two types of certificates. Forward certificates, certificates of X generated by other CAs. Reverse certificates, certificates generated by X that are the certificates of other CAs. Revocation of certificates. Recall from figure 4.5 that each certificate includes a period of validity, much like a credit card. Typically, a new certificate is issued just before the expiration of the old one. In addition, it may be desirable on occasion to revoke a certificate before it expires for one or more of the following reasons. 1. The user's private key is assumed to be compromised. 2. The user is no longer certified by the CA. Reasons for this include subject's name is changed, the certificate is suspended, or the certificate was not issued in conformance with the CA's policies. 3. The CA's certificate is assumed to be compromised. Each CA must maintain a list consisting of all revoked but not expired certificates issued by that CA, including both those issued to users and to other CAs. These lists also should be posted on the directory. Each certificate revocation list, CRL, posted to the directory is signed by the issuer and includes the issuer's name, the date the list was created, the date the next CRL is scheduled to be issued, and an entry for each revoked certificate. Each entry consists of the serial number of a certificate and revocation date for that certificate. Because serial numbers are unique within a CA, the serial number is sufficient to identify the certificate. When a user receives a certificate in a message, the user must determine whether the certificate has been revoked. The user could check the directory each time a certificate is received. To avoid the delays and possible costs associated with directory searches, it is likely that the user would maintain a local cache of certificates and lists of revoked certificates. X509 version 3. The X509 version 2 format does not convey all the information that recent design and implementation experience has shown to be needed. Here we'll list the following requirements which are not satisfied by version 2. 1. The subject field is inadequate to convey the identity of a key owner to a public key user. X509 names may be relatively short and lacking in obvious identification details that may be needed by the user. 2. The subject field is also inadequate for many applications which typically recognize entities by an internet email address, a URL, or some other internet-related identification. 3. There is a need to indicate security policy information. This enables a security application or function, such as IPsec, to relate an X509 certificate to a given policy. There is a need to limit the damage that can result from a faulty or malicious CA by setting constraints on the applicability of a particular certificate. It is important to be able to identify different keys used by the same owner at different times. This feature supports key lifecycle management, in particular, the ability to update key pairs for users and CAs on a regular basis or under exceptional circumstances. Rather than continue to add fields to a fixed format, standards developers felt that a more flexible approach was needed. Thus, version 3 includes a number of optional extensions that may be added to the version 2 format. Each extension consists of an extension identifier, a criticality indicator, and an extension value. The criticality indicator indicates whether an extension can safely be ignored. If the indicator has a value of true and an implementation does not recognize the extension, it must treat the certificate as invalid. The certificate extensions fall into three main categories: key and policy information, subject and issuer attributes, and certification path constraints. Key and policy information. These extensions convey additional information about the subject and issuer keys, plus indicators of certificate policy. A certificate policy is a named set of rules that indicates the applicability of a certificate to a particular community and/or class of application with common security requirements. For example, a policy might be applicable to the authentication of electronic data interchange, EDI, transactions for the trading of goods within a given price range. This area includes the following. Authority key identifier identifies the public key to be used to verify the signature on the certificate or CRL. Enables distinct keys of the same CA to be differentiated. One use of this field is to handle CA key pair updating. Subject key identifier identifies the public key being certified, useful for subject key pair updating. Also, a subject may have multiple key pairs and correspondingly different certificates for different purposes. For example, one for digital signature and another for encryption key agreements. Key usage indicates a restriction imposed as to the purposes for which and the policies under which the certified public key may be used. May indicate one or more of the following: digital signature, non-repudiation, key encryption, data encryption, key agreement, CA signature verification on certificates, and CA signature verification on CRLs. Private key usage period indicates the period of use of the private key corresponding to the public key. Typically, the private key is used over a different period from the validity of the public key. For example, with digital signature keys, the usage period for the signing private key is typically shorter than for the verifying public key. Certificate policies Certificates may be used in environments where multiple policies apply. This extension lists policies that the certificate is recognized as supporting, together with optional qualifier information. Policy mappings, used only in certificates for CAs issued by other CAs. Policy mappings allow an issuing CA to indicate that one or more of the issuer's policies can be considered equivalent to another policy used in the subject CA's domain. Certificate subject and issuer attributes. These extensions support alternative names in alternative formats for a certificate subject or certificate issuer and can convey additional information about the certificate subject to increase a certificate user's confidence that the certificate subject is a particular person or entity. For example, information such as postal address, position within a corporation, or picture image may be required. The extension fields in this area include the following. Subject alternative name contains one or more alternative names using any of a variety of forms. This field is important for supporting certain applications such as electronic mail, EDI, and IPsec, which may employ their own name forms. Issuer alternative name contains one or more alternative names using any of a variety of forms. Subject directory attributes conveys any desired X500 directory attribute values for the subject of this certificate. Certification path constraints. These extensions allow constraint specifications to be included in certificates issued for CAs by other CAs. The constraints may restrict the type of certificates that can be issued by the subject CA or that may occur subsequently in a certification chain. The extension fields in this area include the following. Basic constraints. Indicates if the subject may act as a CA. If so, a certification path length constraint may be specified. Name constraints. Indicates a namespace within which all subsequent names and certificates must be located. Policy constraints. Specifies constraints that may require explicit certificate policy identification or inhibit policy mapping for the remainder of the certification path. Figure of PKIX architectural model. RFC 4949 Internet Security Glossary defines public key infrastructure, PKI, as a set of hardware, software, people, policies, and procedures needed to create, manage, store, distribute, and revoke digital certificates based on asymmetric cryptography. The principal objective for defining a PKI is to enable secure, convenient, and effective acquisition of public keys. The Internet Engineering Task Force, IETF, Public Key Infrastructure, X509, PKIX Working Group has been the driving force behind setting up a formal and generic model based on X509 that is suitable for deploying a certificate-based architecture on the Internet. This section describes the PKIX model. Figure 4.7 shows the interrelationship among the key elements of the PKIX model. These elements are end entity, a generic term used to denote end users, devices, for example servers, routers, or any other entity that can be identified in the subject field of a public key certificate. End entities typically consume and/or support PKI-related services. Certification authority, CA, the issuer of certificates and usually certificate revocation lists, CRLs, It may also support a variety of administrative functions, although these are often delegated to one or more registration authorities. Registration authority, RA, an optional component that can assume a number of administrative functions from the CA. The RA is often associated with the end entity registration process, but can assist in a number of other areas as well. CRL issuer, an optional component that a CA can delegate to publish CRLs. Repository, a generic term used to denote any method for storing certificates and CRLs so that they can be retrieved by end entities. PKIX management functions. PKIX identifies a number of management functions that potentially need to be supported by management protocols. These are indicated in Figure 4.7 and include the following. Registration. This is the process whereby a user first makes itself known to a CA, directly or through an RA. Prior to that, CA issuing a certificate or certificates for that user, registration begins the process of enrolling in a PKI. Registration usually involves some offline or online procedure for mutual authentication. Typically, the end entity is issued one or more shared secret keys used for subsequent authentication. Initialization. Before a client system can operate securely, it is necessary to install key materials that have the appropriate relationship with keys stored elsewhere in the infrastructure. For example, the client needs to be securely initialized with the public key and other assumed information of the trusted CAs to be used in validating certificate paths. Certification. This is the process in which a CA issues a certificate for a user's public key and returns that certificate to the user's client system and/or posts that certificate in a repository. Key pair recovery. Key pairs can be used to support digital signature creation and verification, encryption and decryption, or both. When a key pair is used for encryption-decryption, it is important to provide a mechanism to recover the necessary decryption keys when normal access to the keyring material is no longer possible. Otherwise, it will not be possible to recover the encrypted data. Loss of access to the decryption key can result from forgotten passwords, PINs, corrupted disk drives, damage to hardware tokens, and so on. Key pair recovery allows entities to restore their encryption-decryption key pair from an authorized key backup facility, typically the CA that issued the end entity's certificate. Key pair update. All key pairs need to be updated regularly, for example, replaced with a new key pair, and new certificates issued. Update is required when the certificate lifetime expires and as a result of certificate revocation. Revocation request. An authorized person advises the CA of an abnormal situation requiring certificate revocation. Reasons for revocation include private key compromise, change in affiliation, and name change. Cross-certification. Two CAs exchange information used in establishing a cross-certificate. A cross-certificate is a certificate issued by one CA to another CA that contains a CA signature key used for issuing certificates. The PKIX working group has defined two alternative management protocols between PKIX entities that support the management functions listed in the preceding subsection. RFC 2510 defines the Certificate Management Protocols, CMP. Within CMP, each of the management functions is explicitly identified by specific protocol exchanges. CMP is designed to be a flexible protocol able to accommodate a variety of technical, operational, and business models. RFC 2797 defines certificate management messages over CMS, CMC, where CMS refers to RFC 2630 cryptographic message syntax. CMC is built on earlier work and is intended to leverage existing implementations. Although all of the PKIX functions are supported, the functions do not all map into specific protocol exchanges. Identity management. Federated identity management is a relatively new concept dealing with the use of a common identity management scheme across multiple enterprises and numerous applications and supporting many thousands, even millions of users. We begin our overview with a discussion of the concept of identity management and then examine federated identity management. Identity management is a centralized automated approach to provide enterprise-wide access to resources by employees and other authorized individuals. The focus of identity management is defining an entity for each user, human or process, associating attributes with the identity, and enforcing a means by which a user can verify identity. The central concept of an identity management system is the use of single sign-on, SSO. SSO enables a user to access all network resources after a single authentication. Typical services provided by a federated identity management system include the following. Point of contact includes authentication that a user corresponds to the username provided and management of user server sessions. SSO Protocol Services provides a vendor-neutral security token service for supporting a single sign-on to federated services. Trust Services. Federation relationships require a trust relationship-based federation between business partners. A trust relationship is represented by the combination of the security tokens used to exchange information about a user, the cryptographic information used to protect these security tokens, and optionally, the identity mapping rules applied to the information contained within this token. Key services, management of keys and certificates, identity services, services that provide the interface to local data stores, including user registries and databases for identity-related information management. Authorization, granting access to specific services and/or resources based on the authentication. Provisioning includes creating an account in each target system for the user, enrollment or registration of user in accounts, establishment of access rights or credentials to ensure the privacy and integrity of account data. Management, services related to runtime configuration and deployment. Generic Identity Management System. The figure illustrates entities and data flows in a generic identity management architecture. A principal is an identity holder. Typically, this is a human user that seeks access to resources and services on the network. User devices, agent processes, and server systems may also function as principals. Principals authenticate themselves to an identity provider. The identity provider associates authentication information with a principal, as well as attributes and one or more identifiers. Increasingly, digital identities incorporate attributes other than simply an identifier and authentication information, such as passwords and biometric information. An attribute service manages the creation and maintenance of such attributes. For example, a user needs to provide a shipping address each time an order is placed at a new web merchant, and this information needs to be revised when the user moves. Identity management enables the user to provide this information once, so that it is maintained in a single place and released to data consumers in accordance with authorization and privacy policies. Users may create some of the attributes to be associated with their digital identity, such as address. Administrators may also assign attributes to users, such as roles, access permissions, and employee information. Data consumers are entities that obtain and employ data maintained and provided by identity and attribute providers, which are often used to support authorization decisions and to collect audit information. For example, a database server or file server is a data consumer that needs a client's credentials so as to know what access to provide to that client. Identity federation. Identity federation is, in essence, an extension of identity management to multiple security domains. Such domains include autonomous internal business units, external business partners, and other third-party applications and services. The goal is to provide the sharing of digital identities so that a user can be authenticated a single time and then access applications and resources across multiple domains. Because these domains are relatively autonomous or independent, no centralized control is possible. Rather, the cooperating organizations must form a federation based on agreed standards and mutual levels of trust to securely share digital identities. Federated identity management refers to the agreements, standards, and technologies that enable the portability of identities, identity attributes, and entitlements across multiple enterprises and numerous applications, and supports many thousands, even millions of users. When multiple organizations implement interoperable federated identity schemes, an employee in one organization can use a single sign-on to access services across the federation with trust relationships associated with that identity. For example, an employee may log on to his corporate intranet and be authenticated to perform authorized functions and access authorized services on that internet. The employee could then access their health benefits from an outside healthcare provider without having to re-authenticate. Beyond SSO, federated identity management provides other capabilities. One is a standardized means of representing attributes. Increasingly, digital identities incorporate attributes other than simply an identifier and authentication information, such as passwords and biometric information. Examples of attributes include account numbers, organizational roles, physical location, and file ownership. A user may have multiple identifiers. For example, each identifier may be associated with a unique role with its own access permissions. Another key function of federated identity management is identity mapping. Different security domains may represent identities and attributes differently. Furthermore, the amount of information associated with an individual in one domain may be more than is necessary in another domain. The federated identity management protocols map identities and attributes of a user in one domain to the requirements of another domain. Federated identity operation. The figure illustrates entities and data flows in a generic federated identity management architecture. The identity provider acquires attribute information through dialogue and protocol exchanges with users and administrators. For example, a user needs to provide a shipping address each time an order is placed at a new web merchant, and this information needs to be revised when the user moves. Identity management enables the user to provide this information once, so that it is maintained in a single place and released to data consumers in accordance with authorization and privacy policies. Service providers are entities that obtain and employ data maintained and provided by identity providers, often to support authorization decisions and to collect audit information. For example, a database server or file server is a data consumer that needs a client's credentials so as to know what access to provide to that client. A service provider can be in the same domain as the user and the entity provider. The power of this approach is for federated identity management in which the service provider is in a different domain, for example, a vendor or supplier network. Standards. Federated identity management uses a number of standards as the building blocks for secure identity exchange across different domains or heterogeneous systems. In essence, organizations issue some form of security tickets for their users that can be processed by cooperating partners. Identity federation standards are thus concerned with defining these tickets in terms of content and format, providing protocols for exchanging tickets, and performing a number of management tasks. These tasks include configuring systems to perform attribute transfers and identity mapping, and performing logging and auditing functions. The key standards are as follows. The Extensible Markup Language, XML. A markup language uses sets of embedded tags or labels to characterize text elements within a document so as to indicate their appearance, function, meaning, or content. XML documents appear similar to HTML, hypertext markup language documents, that are visible as web pages, but provide greater functionality. XML includes strict definitions of the data type of each field, thus supporting database formats and semantics. XML provides encoding rules for commands that are used to transfer and update data objects. The Simple Object Access Protocol, SOAP, a minimal set of conventions for invoking code using XML over HTTP. It enables applications to request services from one another with XML-based requests and receive responses as data formatted with XML. Thus, XML defines data objects and structures, and SOAP provides a means of exchanging such data objects and performing remote procedure calls related to these objects. WS Security, a set of SOAP extensions for implementing message integrity and confidentiality in web services. To provide for secure exchange of SOAP messages among applications, WS Security assigns security tokens to each message for use in authentication. Security Assertion Markup Language, SAML, an XML-based language for the exchange of security information between online business partners. SAML conveys authentication information in the form of assertions about subjects. Assertions are statements about the subject issued by an authoritative entity. The challenge with federated identity management is to integrate multiple technologies, standards, and services to provide a secure, user-friendly utility. The key, as in most areas of security and networking, is the reliance on a few mature standards widely accepted by industry. Federated identity management seems to have reached this level of maturity. Federated identity scenarios. To get some feel for the functionality of identity federation, we look at 3 scenarios. In the first scenario, workplace.com contracts with health.com to provide employee health benefits. An employee uses a web interface to sign on to workplace.com and goes through an authentication procedure there. This enables the employee to access authorized services and resources at workplace.com. When the employee clicks on a link to access health benefits, her browser is redirected to health.com. At the same time, the workplace.com software passes the user's identifier to health.com in a secure manner. The 2 organizations are part of a federation that cooperatively exchanges user identifiers. Health.com maintains user identities for every employee at workplace.com and associates with each identity health benefits information and access rights. In this example, the linkage between the 2 companies is based on account information and user participation is web browser based. In B, it shows a second type of browser based scheme. Parts supplier is a regular supplier of parts to workplace.com. In this case, a role-based access control RBAC scheme is used for access to information. An engineer of workplace.com authenticates at the employee portal at workplace.com and clicks on a link to access information at partssupplier.com. Because the user is authenticated in the role of an engineer, he is taken to the technical documentation and troubleshooting portion of partssupplier.com's website without having to sign on. Similarly, an employee in a purchasing role signs on at workplace.com and is authorized in that role to place purchases at partssupplier.com without having to authenticate to partssupplier.com. For this scenario, partssupplier.com does not have identity information for individual employees at workplace.com. Rather, the linkage between the 2 federated partners is in terms of roles. The scenario illustrated in C can be referred to as document-based rather than browser-based. In this third example, workplace.com has a purchasing agreement with pinsuppliers.com, and PinSupplies has a business relationship with eShip.com. An employee of workplace.com signs on and is authenticated to make purchases. The employee goes to a procurement application that provides a list of workplace.com suppliers and the parts that can be ordered. The user clicks on the Pin Supplies button and is presented with a purchase order web page, HTML page. The employee fills out the form and clicks the Submit button. The procurement application generates an XML SOAP document that it inserts into the envelope body of an XML-based message. The procurement application then inserts the user's credentials into the envelope header of the message, together with Workplace. The procurement application posts the message to the Pin Supplies purchasing web service. This service authenticates the incoming message and processes the request. The purchasing web service then sends a SOAP message, its shipping partner, to fulfill the order. The message includes a pinsupplies.com security token in the envelope header and the list of items to be shipped, as well as the end user's shipping information in the envelope body. The shipping web service authenticates the request and processes the shipment order. In summary, we have, in general, remote user authentication principles. We talked about symmetric key distribution using symmetric encryption. We went on to KERBEROS, explaining the difference between version 4 and 5 and why 5 is needed. We've talked about key distribution using asymmetric encryption as well. And certificates, we talked about PKI, and then federated identity management. Well, thanks for listening. Bye for now. From Teacher Todd.